trying to create a non-trivial simple closed curve, right? Because I want to make this phi one inject of the graph. So I would like to say, oh, okay, I got a critical point. So here I have a non-trivial curve, but that's not true with type 1. While it is true with type 2. I mean, this is just because this is the distance function. So because this is what might happen. So I have a critical point, but no non-trivial loop, right? So these critical points are not good. While in the other case, so type 2, I have two holes that come together like that. So I don't know how, yeah. And I have my p that is here. So this curve is always non-trivial. Okay, for this. Yeah.
So you assume that the two loops were already non-trivial in type 2?
Actually, they have to be in this type 2 because, I mean, they come together because, you see, I start with P, okay, so why this loop is non-trivial? Because I have these loops that they intersected only once. So this cannot bound at this. I mean, both this intersect only once. So it's because I have a distance function that these loops, yeah, so this, okay, so what you ask actually maybe, let me give a fairer answer. If this is like that, it's not possible that these two are at the same level, right? Okay? So they are non-trivial, yes. Exactly because it is, if it were just any Morse function, of course this wouldn't be true. Right? So I use this fact here. And I understand this was confusing, so that's why I came back. Why I distinguish between the two. But okay, so I have this equality, and now I know that I have many, so that's the point, I have many of the type I like. And then the next step was, as I said, to take slices, and actually, here there is a slight mistake, so I said I take only the type 2 critical values, but actually, P0, the first critical value is fine, because I said I have P, and now P lies on the systole, so the first critical value will give me a non-trivial loop too. Right? It's going to be of type 1, not of type 2. But because P, I chose P to lie on the systole, so the picture is like that. And this gives me, this point also here gives me a non-trivial loop. Okay, so for the moment I forget the first slice and I look at the further slides. And as I said, I look at the slice there, and there are some loops that are non-trivial and some loops that are trivial. So to construct my graph gamma t, to construct my graph gamma t, I only take the non-trivial one, so these ones I forget. And I add to it arcs that come from these type 2 critical points. So I have arcs that go like that, and the arcs lie in the next level. So to be precise, I don't have one graph at each level, right? So at each level, from this to this, I get from this to this. For every t, I have a graph, right? So I have infinitely many graphs, and this is what I'm going to use. This is how I'm going to use the covariant. Okay. So this is the construction of the graph that I explained also last time. So we add the arcs, and now we want to show that for the graphs I constructed, so the systole is greater in the graphs than in the surface. And now, in fact, I said the fundamental group invades, but that's not what I'm going to prove. This is a bit more than what I will prove. I will just show that that these loops are not, that if I take a simple loop, so I'm not just going to take any element of the fundamental group, I'll just take a simple loop in this graph, and I will show that this is not contractible in sigma, in my surface. So there are two cases. Either the loop is contained in f inverse of t, so it's one of my green loops that I drew before, and then by hypothesis I just took them to be non contracted, or, well, they contain some other piece, right? So the case 2 is I have my simple arc is some arc and contains some, I don't know what the loop is, but it contains, well, maybe I'll make a very simple picture, so maybe it is this, right? So it's going to contain some red loops, right? Some red pieces of the loop. So there are these loops and it contains some pieces. Okay, so maybe I'll draw one more picture here. So I have my loop in the graph, and then, I don't know, maybe there are many of the arcs, and now, okay, it should go back somehow, right? Anyway, so these are the arcs that appear, and maybe I should erase this to make it more believable that this is a loop. So maybe this is the loop, it goes around and so on. So this is my loop. And now I want to show that this is not contractible. So it's the same as to say this doesn't bound the disk, right? So I have my loop gamma as, yeah, so this is my loop gamma, and now I'm going to focus on the highest. Yes. So on the highest one of these red arcs. So there is one that for which the corresponding t is the highest. Okay, let's say that my loop gamma bounds a disk, right? So it's trivial. Well, if you see what happens at this critical point, I have to. So at this critical point, I have these two simply closed curves, right? Because I get something like that. So these two simple closed curves are, yes, these two simple closed curves. And now both of them are non-trivial, right? Okay, but if this gamma is a disk, one of these simple closed curves is going to be inside, and the other is going to be outside. So this is going to bound the disk, which is a contradiction. So just look at the highest level, and you see if my gamma bounds a disk, then one of these two simply closed curves that intersect tangentially, so to speak, gamma bounds a disk, which is not possible. So say gamma bounds a disk is one of, sorry, I denoted the beta 1, beta 2. These are beta 1 and beta 2. So it doesn't, okay, and right. Okay, so now let's say that I have, say, at the level k, I add k arcs. And then I have actually this is wrong. So the sum is G. I mean, I thought that the first one was type 2, but it is type 1. So I have these inequalities. I have that the sum of G is, first of all, the Betty number is greater than Gk plus 1, because you see every time I add an arc, the Betty number increases, right? So if I add Gk plus 1 arcs, then the Betty number is Gk plus 1 because I already started with at least one simple closed curve. And if I sum up in all levels, I get G. Okay. So this is what will allow me. So remember, G is a very big number, and this is what allows me to bound the complexity of these graphs. Okay. Now, if for some t, okay, so this is arbitrary inequalities, right? So as I said before, if I have big complexity and small length, then I'm done, right? So small length, I will just take it to mean there is no reason for this time, right? I will just take it to mean this. So if the length, so originally I stated the inequality where the length was exactly gj, but if it is of the order of gj, then by the systolic inequality I am done, because I get a small loop in gamma k. Okay, so recall, so what I'm using here is that the systole of gamma is less than that. So if I apply this there, so the length is, so let's do the calculation again. So the length is 10 gj. Oh, the constant here was 5, right? And then I have 10 gj divided by the Betty number, which, well, it's gj plus 1. Let's just make it gj, and then, since I use inequality, and then I have log gj. And then I had also 5, right? This constant 5. So I correct my constant from last time, it's 50. So this gj cancels with this gj, and I get that the systole is bounded. Okay, so okay, so if one of the lengths is small, if one of these lengths is small, then I'm done. But the problem is maybe there is not even any graph there. Perhaps everything happens at the first level, right? So I have to deal with the first slice, and the first slice is different because you see, when I started with these graphs, I said, okay, I'm going to pick all the non-contractible simple closed curves. But in the first slice, there is no such simple. Okay, maybe let's see where I do this. So the first slice, as I said, is different because the simple closed curve there is contractible. And why is that? Well, here is my P, right? And this is where I get my first slice. And of course, when I'm below this, I'm contractible. So above that, there are non-contracted curves, but this is contractible. Okay, so I'm stuck, so to speak. But the solution is simple. For this, instead of using this simple closed curve, I have this geodesic from P that goes to the first critical point, and I'm just going to replace it by 2, right, which are not much bigger. So I'll just replace my arc by this arc here, and this arc there. And then this problem disappears. Okay. Okay, so this is what I say here. So I have LT, and I take this arc. So this is the arc beta in my previous picture. So this is beta. This red arc is beta, and I call this LT. And one piece of this is KT, and the other is there is MT. So I'm just replacing this curve by 2 curves, and then I can use the same argument. I add arcs to these new curves that are non-contractible, and now I'm ready, after dealing with this technicality with the first slice. Okay, so let's say that the length doesn't make me the favor to be small, and it's big, right? Well, the length of this graph, say, is big. Well, then the length of LT has to be at least greater than 60J, right? So, because remember, my graph had a part, so this goes LT, the union of those LT, and this was the arcs that I added, and I was careful to add the arcs on the next slide. So this has length 1, and the next slide has length 1 again. And I took parts, so maybe, so this has length 1 up to here, and then the next part. And I didn't take arcs there, I took arcs from the following slide there. So this has length 2 plus 2, at most 4, right? So this is what makes that every add, so I add GJ set arcs, so all in all I take out 4 GJ length, right? So what is left is greater than 6 GJ. Okay, so if we know slice, I have small length, then I use the co-area inequality. I have that G, which is the area of S, is the integral of this LT, which is greater than 6G minus 6, which is a contradiction, of course. So this finishes the proof. Are there any questions? Yes?
So in this covariant inequality, so what this means is that one of the gamma kT's must have bounded length.
Yeah, small length, like smaller than 10 GJ.
Yes. So that one is short. But and then gamma kT is supposed to be the union of the non-contractible loops in that slice plus a few arcs, right? But how do we know that in that particular gamma kT that is short, there are any non-contractible loops? Why might that slice not be be composed of loops that are all contractible?
I mean, this is what okay. So first of all, I mean, after I'm in the critical level, so I did this between all the critical points of type 2, right? So I didn't do it in every step. So you are right. I mean, if I had sliced the whole surface, but I didn't do that, right? So the surface could look like that. Okay. So it could be here, 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 and then I could, if I continued sliced or above this level, right, I could have trivial loops. But between this part where I sliced, there is always at least one non-trivial loop. Okay. Only above that, there is a risk. And so this is the risk I faced in the first slice. So the first slice had exactly your problem. I had a loop, but it was trivial, so I had to do something, right? And this problem will appear again after the last type 2 critical point. I will have something that is not trivial. But before that, everywhere, I have, exactly because I have this, because I have this loop going. So every time I have a type 2 critical point, I have this loop going like that, and then it intersects. So you know this creates another loop that is non-trivial. Okay. So there is below this level there is always a level something that is non-trivial, but not below the first critical point. Yeah, I mean if at some point, okay, or to say it differently, if at some point what you say happens, right? So say all my loops are trivial, that means that after this, my surface is like that, right? So there are no type 2 critical points, okay? So this, what you say does happen, but that's why I restricted my slicing between the type 2 critical points, okay? This of course can happen. And I can have type 1 critical points, I don't mean I need type 1 critical points, but I'm not going to have type 2 critical points if something happens. Okay, other questions? Yes?
Am I right by saying that the only thing we used from structure of the metric on the manifold is the area inequality?
Yeah, and basic stuff like differential topology, I mean Morse theory and so on, yes. The area inequality is the only thing that this uses. Really.
I mean, can it be applied to some other type of metrics and manifolds, like Riemannian or whatever?
I mean, similar things, certainly you don't need Riemannian metric, right? Now for other type of metrics, I'm not familiar with every type of metric to be sure, but if you have a metric basically where the area inequality applies, this proof will work. Okay? That's all you need. It doesn't have to be smooth, certainly we didn't use smoothness. And any more questions? Okay, so Saburo used actually the same method much later to show that we can bound the length of the shortest separating loop. So you see, we gave a bound for the systole, but maybe the shortest loop looks like that, right? And the question is, can we have a bound on a loop that actually separates, right? Something like that. So this is a separating loop. And what do we need for this? Actually, we can use the same strategy. Before we produced a single small loop in in the graph gamma t. Now to prove Saburow's result, we just need to have two small loops, because then we take their commutator and we are done. Right? The commutator is separated. Okay, so we just need two small loops based at the same point. So it's similar. And now, well, of course, you can ask the same question if you can have these two small loops in graphs. And of course, this works. If you have a complicated graph, you can always find two loops close to each other. So this is one thing you use. And the other thing, of course, is that in this case, one really needs pi1 of gamma to embed, so that you can take this commutator and be sure that it's still okay. So it's a bit more technical, but it's the same strategy. Okay, how about spheres? Well, there is Krog's result that says that the length of the shortest geodesic on the sphere satisfies a similar inequality. So we can bound the constant. I'm not sure this is, well, certainly what I wrote there is not the best constant. And it is an open question whether Loewner's bound holds for every surface. So, for example, this is known for g equal to 2, surprisingly. So we know that if we have a loop there, I mean, we know that the systolic inequality here in a surface of genus 2 is better than the systolic inequality, is at least as good as the systolic inequality for the single torus. But if we start increasing the holes, surprisingly it gets harder. So it's not clear that the systole of this, where we fix the area 1, is smaller than the systole of this. Okay, and in fact, this is known, well, asymptotically we know it, this is what we just proved, right? That the systole goes to 0 as we go to infinity, but it is only known for g greater than 20. So either for genus 19, you have 19 holes and you don't know if the systole is smaller than in the case of the torus. Okay, but now apart from the systole, of course, one can think more globally, or one can think of other properties of the geometry of surfaces as the genus goes to infinity. So what can we say? There is a classical conjecture, Berger conjecture, which somehow gives a more global understanding of the surface. So the conjecture is that SG always, so I remind you what is a Pans decomposition. So we have a surface, and now a Pans decomposition is a collection of simply closed curves that decomposes the surface into pairs of Pans, so spheres with 3 holes. So you can think the sphere of Pans, I guess. Okay, and so we can always cut the surface. Well, I'm not going to draw all of them. So I'm saying that this, I call this cutting curves, these curves that decompose it. So it's just a maximal collection. If you don't like that, it's just a maximal collection of disjoint, simple closed curves in the surface. So I take such a maximal collection and I want to minimize the maximal length. And the conjecture is that this is bounded by constant square root the area. So where does this come from? Maybe, well, just think of a sphere. Well, sphere, of course, has no topology, but then add, so this has area A, and then this has length square root A, but now add many small handles here, everywhere. Well, you see, I mean, it's intuitively obvious that if I fill this with handles and I'm going to take a Pans decomposition, I'm going to need at least square root A, right? So, is there anything worse than that? It seems to be a very hard problem. I mean, understanding globally it has been open for a while.
So is it a question just for, is it enough to...
Oh, I mean, probably, okay, I'm not sure if this is in the literature, but it seems very reasonable that if you prove it for hyperbolic, you will prove it for all, but you just state it for all, right? Yeah, I mean, it's open even in the hyperbolic case, but it's likely that these two are equivalent. I don't know. Actually. Yeah.
And a question.
Yes.
So you're mentioning that Saburo was looking at the length of the separating curves. Can one not just apply that? Keep separating and separating using curves of that length bounded by square root of area until we get pans, or is that not? Does that not work?
Oh, well, we don't know. I mean, after we cut the first time, we have no theorem because we have a surface with boundary, right?
Okay.
So we have no theorem after the first cut to apply, and then exactly this is the problem. If we can keep going by small curves, that's the question. Yeah, I mean, this is what we don't know. Basically, if you like, we understand the surface very locally. We know at some point it has something small. But after that, I mean, and I guess one can do, and I think there are results like that where we can find 5 or 10 small curves or something like that. But after that, we are stuck. We only know a small piece of the surface. We can say something about a very small piece of the surface, but globally, we don't understand.
What is the difficulty of having a boundary component?
I mean, first of all, the systolic inequality doesn't work, right? I should have remarked that earlier. I can have something of very small area. Well, maybe you won't like this example, but this has very small area, but very big systole, okay? Right? So yeah, no systolic inequality when we have boundary. I should have remarked that. So after we create boundary, we're stuck. Okay, any other question?
But cannot you just close the boundary?
I mean, if you think Boozer conjecture is easy, I don't know what to say. I mean, to this, the problem is that as you add curves, so you have a small curve, fine. But as you add more and more curves, you make it harder for you to add disjoint curves. You create an obstruction, right? I don't know how to say it. You create an obstruction with these curves that you added. You started adding curves, and maybe you even didn't do an optimal thing. And now it's harder. Every time you add a curve, it gets harder to get another curve. I mean, this example maybe it's a bit trivial, but yeah, it illustrates that there is no general inequality when you have boundary. Okay. So this is, yeah, the first time you see it, I mean, the first time I saw it, I was shocked. I thought, okay, when there's don't surfaces, and very naively spent even some time trying to prove it. So, but okay, so there are some positive results. So what is the Ziegler constant? Maybe you have seen it, is the infimum. So the Ziegler constant intuitively tells us how easy it is to cut a big piece of the manifold. Okay, so this is, so the problem is so a bound of the Ziegler constant tells me, so if I have a small Ziegler constant, it tells me that I have a manifold and I can cut a big piece of the manifold with small cost, right? And this quotient just expresses how easy it is to cut a piece of the manifold with something that doesn't have big, so say this is of dimension n, so how easy it is to cut a big piece of the manifold by something that has small n-1 area, right, by a hypersurface.
Can I have a question?
Yes?
Wow. You're saying it must be a big piece, but you have inequality that it's less than half of the manifold. Why is that inequality there then?
Well, I'm taking, right, well, first of all, what I said is not quite true, because you can have a small Ziegler constant, you're going to have something like that, but the inequality is there actually because I wanted to define, and I shouldn't have done that, even for non-compact manifolds. Sorry. Okay, no, because I say you cut a big piece, so I'm just calculating the quotient for the big piece. So of course, if I calculate, so if I do this cut, and I calculate the quotient of this over this, it's going to be small, right? Okay?
Okay.
Right? So I say, okay, no, you have to look at the small piece. Right? That's what this says.
Ah, okay, I see.
Okay? Right? Yeah, sorry. Okay, so, yeah, I mean, I want to cut a big piece, so I look at the smaller piece, not
Yes,
the big
of
piece.
course, yeah.
Otherwise, of course, this is going to go to 0, right? Okay? I will just take, that's why we have, thank you. Okay. Okay, so for example, some positive results, the Ziegler constant of the sphere, so if I take any Riemannian metric on the sphere, the Ziegler constant is bounded. So, and now again, we have to normalize, right, because in this quotient, if you see, there is no square root or anything, so, so let's normalize. So when I say it is bounded, I mean normalize, take area. So I have any Riemannian metric. So when I say, so again, I'm in the setting of curvature of free geometry. So of course, if you fix a manifold, you have a bound. If you fix a metric, you have a bound. But I want to have a bound that doesn't depend on the metric. Okay? So I fix a topological type. I take a sphere. I take any Riemannian metric on it. I normalize the area. So normalize area of S2 is equal to 1, and I claim I can always cut a big piece with not much length, okay? And now this is actually the general case of surfaces. It was proved by Yang and Yao for all SG, and it was known earlier for the sphere, sorry, now I don't remember the exact reference. So I'm going to give a proof of this. The classical proof is analytic, it uses the eigenvalues of the Laplacian, but I'm just going to give a direct geometric proof of this. So why the Ziegler constant is bounded. Okay, so take the shortest simple closed curve. So proof. So this goes in the 80s. Take a shortest simple closed curve bounding omega with area of omega greater or equal to 1/4. Okay? Now, now you might object there is no shortest, possibly. And I don't care actually, I will just take something that is close to the shortest. I mean, it's not exactly shortest, but it's epsilon close, very close to the shortest. So I don't care about that. So here is my sphere, and here is, let's call it gamma, that cuts this piece. And I want to, bounding, the Ziegler constant is equivalent to finding a bound on the length of this, okay? So now what I do is, so this is omega. Now I'm going to use as the complement, to think of the complement of omega, let's say omega 1, I don't know. And see what I can say about its area. Okay, so I know the area of S2 is 1, of course, so the area of omega 1 has to be 1. And now let's say gamma is very long, right? So let me draw another picture. So I have my gamma, and I have omega 1 there. And now I'm going to cut gamma into 4 equal pieces. And now note, the distance of these pieces in omega 1 has to be big. It cannot be small, because if it is small, then I can shorten the curve. So it has to be bigger than, so okay, I'm not sure. So this distance is greater or equal than the length of gamma over 4. Why? If it is not, then I can just replace the original curve by adding this arc and forgetting the big piece, right? So I can replace, if it's not, I just replace gamma by this blue curve, right? and I still, okay, either this or this, and one of these two pieces is going to be bigger than 1/4. So I'm still okay. Right? So these sides have to be at big distance, L gamma over 2, but then Besicovitch inequality implies that the area of omega 1, so which is again a consequence of the co-area inequality, is greater than something like lambda well, might even be bigger than that, but certainly greater than that, which is L squared gamma over 16, and we know that this is less or equal to 1, so I get that L of gamma is less or equal to 4, which gives me a bound of the Ziegler constant. Now here, I use Besicovitch inequality, which I think we saw in a previous lecture, but it says that if I have a Riemannian square, well, square, I mean just a curve which has 4 sides, so if I have a Riemannian square, such that this distance is greater, the distance of the opposite sides is greater than A, and this distance, well, can I take B? Well, anyway, I'll take A both. So if we have this, then the area is greater or equal than A to the 4th. And how do you prove that? We can just use co-area inequality, right? Just take level sets and you integrate, and you get A4. So maybe I'll leave that as an exercise, so basically. Exercise. So in proof is use co-area inequality. Okay, so H of S2 is bounded, and the same. Okay, so this is the theorem, and this is what we just said. Sorry, something went wrong with my slides. Okay. Okay, so, okay, yeah, I was missing. So Scherz gave the bound for the two spheres, and Yang and Yao generalized this to a surface of bounded genus. However, the bound they found goes to infinity to infinity as B goes to infinity. So we get worse and worse bounds as the genus increases. Okay, so and the same proof, actually, this geometric proof also works to show an inequality like that. Maybe not optimal. There is there are better bounds that were found later on by Korevar on this. Okay. So we have a bound for the Ziegler constant, and now I say that the Ziegler constant goes to infinity, and one way to see that is using expander graphs. So let gamma be a graph, then if we have two sets, S and T in the graph, I denote by this the number of edges between the two. So this is EST. And now the edge boundary of a set is just the number of edges that go from a set of vertices that go from S to the complement of S. And a graph, a K-regular graph, is a C expander if for all subsets with cardinality less than V over 2, the boundary of S is has at least as many edges as the set of vertices times a constant. Okay, so morally every subset has a big boundary. So this is an expanded graph, and it is known by result of Pinsker that there are 3 regular C expander graphs for n large enough. So as n goes to infinity, we get a sequence of expanded graphs for some C. Okay, so C is just the same for all these graphs, for all the sequence of graphs. And now we can use these expanded graphs to show that that the constant Cg is not just an artifact of the proof. The Finger constant does go to infinity as G goes to infinity. So why? Okay, well, of course, there is, so again, I'm going to normalize. So the area of SG is going to be equal to 1, right? The genus increases, but my area is fixed. And I want to show now that I cannot cut the surface. Well, you might, well, I haven't created the surface, but the surface you can guess how I'm going to create. So I have my expanded graph, and now I'm going to replace, and there is flexibility in how you do that. I'm going to replace each one of these with a small sphere of with say 3 holes. So each vertex is going to be replaced by an appropriately sphere with 3 holes. And now you can just, every time you have an edge, you can either glue the holes or add a small cube, it doesn't matter, to join this, okay? And now what is the idea? Well, of course, you're going to say, if I cut a big piece of the surface, then this costs a lot, right? So so there are 2 ideas here.
Sorry, which surface are we looking now at? So what is the set of surface or metrics that we are considering here?
Okay, thank you. Yes, you're right. I mean, if you say something about the metric. So here I just take the standard sphere in R3, right? Or actually the standard Riemannian sphere, right? Of area equals 1 over n. So it has huge curvature. And I take 3 holes which are at some distance, are regularly spaced. And if the radius of this is, I mean, I take them so that these distances are comparable to their diameter, okay? So I take a sphere with area 1 over n, so the standard sphere, the standard metric of area 1 over n, okay? And I replace every vertex by this, and when there is an edge, maybe I just glue the corresponding simple closed curves, and well, I have to change a bit the metric to make it smooth, so I do that. Okay, so this is the surface. And now, of course, I want to use the fact that these are expanded graphs, and I said that the Ziegler constant of a sphere is bounded, but this was a slight lie, because you see when R is greater than 1, so there is this trivial observation that this is what makes this proof work. If R is greater than 1, then R squared is greater than R, right? So when I take something like R over R squared is small, right? It's smaller than 1. But if R is less than 1, if I take, so like here, my area is very small than 1, if I take this, the boundary of this curve, the length of this, so R over R squared is huge, right? So close to infinity, okay? So one way to bound the Ziegler constant, for example, would be, okay, focus on one of these spheres. If these spheres were big, yeah, I could cut a big piece and so on, but since these spheres are tiny, the area is much smaller than a curve that bounds something there, right? So now, if I try to take a region, so I have my sphere, my SG, and I try to find a hypersurface. Well, I'll just do it like that, where the area, the length, so the hypersurface is just a collection of simple closed curves. So let's call this gamma. So it's not connected, right? Sorry. So I want to find the bound length of gamma over area of omega. Okay. Okay. Let's see. If omega contains entirely in its interior a lot of the spheres, it contains a lot of its vertices, right? Okay. So So I want, okay, so again, to bound the Ziegler constant, I want, so the area of SG is equal to 1, and I want, so fix epsilon. I'm going to show that I cannot cut even a piece of area epsilon, and now I want the area of omega to be greater or equal to epsilon. Okay? And now, if I have a lot of curves of these vertices entirely contained into my domain omega, well, then by the expander property, I know that the boundary of this, I mean, I have a lot of edges, so to speak, coming out, and I have to contain in gamma. So when I say a lot, I mean, let's say that the spheres inside, have total area entirely inside. You have total area greater or equal than epsilon over 2, right? Okay. Then I know that I get a big boundary, right? I have a lot of boundary, and the boundary is all big because of this remark that R is much bigger than a square. So I'm going to get a huge length on gamma. Okay. Now, okay, maybe I have very few spheres entirely contained inside, and I have many spheres that are partially contained, right? So I have many spheres that are not entirely contained in omega, but partially contained. But as I said before, to cut a reasonable piece, a reasonable proportion of these small spheres, it costs a lot. So again, I end up with huge gamma. So in both cases, no matter where, how I'm trying to create this omega, I have a huge length on the boundary. Okay? So that's...
Do you get similar asymptotics as in the theorems of
Oh no, I didn't try to... I mean, the theorems, first of all, there are no... these theorems have nothing to do with this asymptotics, right? Because, I mean, it's just an arbitrary bound. So, so we showed that the Ziegler constant is less than C. If you ask whether the optimal asymptotics are known, I don't know, but the previous theorems just showed this inequality, right? And now I'm explaining something else. I'm explaining that CG, if CG is the optimal constant, is necessarily goes to infinity, right?
Yeah, but I think so that the previous theorem was constructive, more or less.
No, the previous, I mean, there are two types of theorem. One is to get an upper bound, and the other is to get a lower bound.
Yes.
So they showed an upper bound, right? But what I'm showing here is a lower bound.
Sure.
Okay?
But you're pretty constructive, yeah?
Here, yes, this is constructive.
Yeah. And the other, the theorem of...
No, the theorem was for the upper bound, not for the lower bound.
Yeah, the upper bound is also constructive. No?
Oh,
So
it's Sarnak's construction gives better probably a lower bound than this, right? So Sarnak, so this is a construction. It's different. It's not Yang Yao. That's I'm trying to make clear. It's not Yang Yao. It's Sarnak, and maybe it was known before Sarnak actually. But probably it was known before. I think it's Brooks, and in fact it's probably Buzer essentially because Buzer came up with the same idea. So Buzer, I should attribute that to Buzer actually. So the previous proof, I'm happy to take credit for the sphere, right, for this geometric proof, but Buzer realized the connection between expander glass and surfaces, and yeah, he proved some things about it. I don't remember if he proved exactly that, but this goes back to Buzer. And now one can even use this to prove that we can have no bound for the 3-sphere, right? Because so if you have bad news for surfaces, it's bad news for everything in higher dimensions, because start with an expander, right? So go from an expander to a high genus surface, something like that, and then just fill it, just make it a handle body. So instead of taking spheres, takes balls, and the same proof, R cube is much bigger than a square, really. So the same idea shows that handle bodies are also bad, right? But now this handle body seems it has a fundamental group, but you can kill the fundamental group and it costs nothing because you have all these simple closed curves there, but you can fill them by something which has arbitrarily small area, right? Because you just have a metric there. I mean, you have nothing basically. You can, if you like, you can even collapse this curve to something like that and smoothen out. So it costs nothing, and you add no volume to this, right? If you do that, you add no volume, and you get a ball that has unbounded Ziegler constant, as big as you like. And now you can just double the ball and make it smoothen, and you get a sphere that is very big. Okay, so there are such examples, different such examples were constructed earlier by Burago Ivanov. But yeah, my point is that from expanders you go to surfaces and you go to spheres, to 3 spheres, and you still, yeah, so let's see where. Okay, maybe I'll give a more recent application of this sort of construction on the isoperimetric profile. So Panos and Narduli noticed that there is a 3 manifold with discontinuous isoperimetric profile function, and they asked if we can build a surface like that. And now the isoperimetric profile is something that comes similar as the Ziegler constant. So is the n minus volume of the AM of T is the n minus 1 volume of the smallest hypersurface that encloses a region of volume exactly equal to T. Okay, this is the isoperimetric profile function, and you can define it for closed manifolds or for... So for closed manifolds, this function, so don't worry, it is continuous. But the question was, so here I give the formal definition, the question was whether it is continuous for any manifold. And now, in fact, there is such, and how does one construct it? One takes a sequence of closed surfaces with Ziegler constant going to infinity and area equal to 1, and join them by very thin cubes. And if you do this construction and you do the calculations for the isoperimetric profile function, you see that you get a discontinuous function. Okay? So maybe I will stop here. Are there any questions? I think there is a photo to be taken. So.
Yeah, thank you very much.